And as always, I'll do my best to post this recording to my YouTube channel. Okie doke. So last class we kind of left off here, Chemistry 3101, looking at question 15.15. And then I asked you to also take a look at question 15.17, but we're going to start over here. And you have to know the N+1 rule, okay? And N+1, N stands for neighbors, is the way I think of it. And so I'm going to circle or put a box around some protons here. And, well, first thing you notice with this compound is that there's a plane of symmetry running through it, right? So you can see that if you rotated this compound 180 degrees, you'd end up with the exact same thing. You would not be able to tell the compound had been manipulated in any way. And so let's say we take these two protons here, this methylene and this methylene. I think that everybody understands that those are chemically equivalent. Give me a thumbs up if you're with me. Those are chemically equivalent because we have an axis of symmetry in the molecule. Okay, cool. So let's say we just pick one of them because they're both going to have the same splitting effect because of the plane of symmetry. But could anybody tell me, would these two protons, would this show up as a singlet, doublet, triplet, or quartet? It's going to be one of those. Could anybody tell me? We go to the neighboring carbon, which is going to be this carbon over here. And this carbon has 1, 2, 3 protons attached to it. If we look at the carbonyl carbon here, that has no protons attached to it. So we do N+1. We do exactly, thanks, Sean. We do N+1. So that means we have 3 + 1, which equals 4. And so we get a quartet. And of course, for these two protons over here, we're going to get the same quartet. Oops, that wasn't supposed to do that. They're going to be overlapping, okay? Nothing more than just an overlapping quartet is all we get. So we'd get a quartet, but it would integrate, and it would represent a total of 4 protons because you have 2 + 2, right? 2 protons here and 2 protons here. But again, both of them would give you the same quartet. It would just overlap, all right? So what if we pick the 3 protons? So what if we pick these 3 protons here, which are chemically equivalent to these 3 protons on this methyl here? What kind of splitting would we observe for those? Could anybody help me out with that? Would it be a singlet, doublet, triplet, or quartet? For those 3 protons, what should I get? They're next to how many protons? It should give you a triplet, right, Savannah? Right, because they're next to 2 protons. So we have N+1, and that gives you 2 + 1. So that equals 3. So you get a triplet. Okay, so you get a triplet for both of those methyl groups that I have in the box with the black ink. So let's say I take this methyl group here. This is a methyl group, but it's not chemically equivalent to the 2 in the black boxes. Okay, so this one in the green box here, could anybody tell me what kind of splitting we would get for this? There's 3 protons here, and how would they be split? Would it give you a singlet, doublet, triplet, or quartet? Could anybody tell me? You'd get a doublet, wouldn't you, Ariana? Right, exactly, because here you have 1 proton, right? 1 proton there. So you end up with N+1. So we get N+1, and it's 1 + 1, which equals 2. So we would get a doublet. Exactly. And then for the last one, I'll put it in a blue circle. Okay. For this methine proton, it's coupled next to 3 protons. So you get N+1 equals 3 + 1, which equals 4. And so that would give you a quartet, right? That's the N+1 rule. Remember, you can only go 2 to 3 bonds away, right? So if you count, like let's say you drew in one of these protons here, you would count, I'll get my yellow pen, 1, 2, 3 bonds away, right? If you were to try to say, well, maybe the proton in blue is coupled next to one of the protons in red. Well, no, that's impossible. So if I draw this proton in red here, let me just eliminate that. If I draw that proton in red, okay, this cannot be coupled to the proton in blue. Why? Look, 1, 2, 3, 4. It's too many bonds away. We only get 2 bond coupling or 3 bond coupling. Give me a thumbs up if you're with me on the number of bonds. Yes, everybody with me on that? Okay, good. All right, and the next thing I want to review with you is just the words. So just to reiterate, when you have a CH3 group, that's called a methyl, right? When you have a CH3 is a methyl. When you have a CH2, that's called a methylene. And when you have a CH group We call that a methine, I-N-E. So the blue one would be a methine. The green and the black, those would be methyls, and the reds, those would be methylenes. Okay, so I'm going to use those words a lot today, probably. So I want you to be aware of those, especially when we get into depth 90 and depth 135 experiments. If you read the entire chapter, you'd know that methyl, methylene, and methine, those words come up quite a bit in this chapter. Well, before we go to the next problem, let's just go back and do a tiny review here of some of the most common splittings that we see in this class. And the first one is an ethyl group. Okay, the first one is an ethyl group. If you have an ethyl group, remember an ethyl group is CH2, a methylene, and then methyl, right? So the methylene is going to give you a quartet because it's coupled next to 3 protons, and the methyl is going to give you a triplet, right? But the triplet should integrate for 3 protons, and the quartet should integrate for 2 protons. So if you see a quartet that integrates for 2 and a triplet that integrates for 3 protons, that's a dead giveaway that you've got an ethyl group. In last class, we covered coupling constant, and we said that if two sets of protons are splitting each other, right? If the n+1 rule applies to a set of protons, that means the distance between the actual peaks has to be the same. We call that the coupling constant. So you might look at this thing here and say, well, I've got a quartet and a triplet. That's an ethyl group. Impossible. It is not an ethyl group. And the reason why is because the distances between the individual peaks is different. They have to be the same as you see up here in order for it to be an ethyl group. And that goes for any kind of group, whether it's an ethyl or an isopropyl or what have you. So let's take a look at the next one, which was the tert-butyl. You can see all my scribbles on here from the last class. But if you get just a big old singlet that integrates for 9 protons, the only possibility would be to be a tert-butyl group. And then last class, we also reviewed the isopropyl group. So isopropyl group, you got to know what an isopropyl group is by now. And we see that the 2 methyls are chemically equivalent to one another. So that's a total of 6 protons, and they're only split by the 1 proton in that methine, the one in the red circle. So you get 1 plus 1, which gives you a doublet. So if you get a doublet that integrates for 6, and then you get a septet that integrates for 1, well, then you've got an isopropyl group, right? Why do you get a septet? Because the methine proton is coupled to a total of 6 protons, and 6 plus 1 gives you 7. Any questions about the n+1 rule before we move on to the next problem? Anything about that? Okay, so let's move on to question 15.17, and then I'll come back to complex splitting. So let's go down here, question 15.17. Here it is. It says, below are some NMR spectra. Identify whether these compounds are likely to contain an ethyl group. So remember, an ethyl group is CH2, CH3, right? An isopropyl group. So an isopropyl group is a methine that has 2 methyl groups attached to it. And then, it's not very pretty. And then a tert-butyl group. Well, I know you know what a tert-butyl group is. It's when you have a carbon that has 3 methyl groups attached to it like this. Okay, so if we look at the first one, if we're looking at A, you can see you've got a multiplet up here around 7 that integrates for 5 protons. You've got some splitting here that integrates. So this 1 on top, that means that represents 1 proton, and this 6 over here means that it represents 6 protons. They gave us a molecular formula, C9H12. Could anybody tell me, do you notice any of the groups here, ethyl, isopropyl, or tert-butyl? Any of them? Yeah, it would be an isopropyl group, wouldn't it, right? Here we have an isopropyl group, so you could write that down. I'm just going to erase all the other spinach that I put here just so we don't confuse ourselves, okay? So there we go, well, something like that. So we definitely have an isopropyl group, right? This is the methine of the isopropyl group, and then these are the 2 methyl groups here, so you can put CH3, CH3, but collectively they make an isopropyl group, which is this, okay, here, like that. Let's keep talking about this problem just for a few more seconds. If I have 5 protons over here, well, if you tally up 6 plus 1 plus 5, what's 6 plus 1 plus 5? It gives you a total of 12. So we know the integration is dead on for all of the protons here. Now, I'll ask I'll ask anybody. If I have 5 protons up here around a little between 7 and 8 parts per million, what kind of functional group, or what do you think about these protons? What kind of protons would these be if they're right between 7 and 8? We talked about this last class. If you have to go over to the sheet that has the table of NMR NMR signals, could anybody tell me if I have 5 protons in between 7 and 8? Yeah, it's going to be an aryl group, right? So that means you've got an aromatic ring. Thanks, Sean. Absolutely. It means you've got an aromatic ring. So let's write that down. Okay, so we've got an aromatic ring like this. Now, I'll really go back into the nether regions of time. If you have a compound with a formula of C9H12, it's got an HDI of what? Does anybody remember that formula? I'm not going to go over it right now, but you could use the formula. Can anybody calculate it in their head, the HDI? So if you have 2n plus 2, it would be 20. 20 minus 12 gives you 8. 8 divided by 2 gives you a total of, it's 4. So the HDI for this compound is 4. All right. What's the HDI for an aromatic ring? What's the HDI for an aromatic ring? Well, you have 1 pi bond, 2 pi bonds, 3. So that's 3, but then you have a ring. So that's a total of 4. So the HDI for an aromatic ring is 4. So there you go. Now we know the structure of the compound. The compound must be this. It's got an aromatic ring and it has an isopropyl attached to it. This is the only possibility for the compound. There's no other possibility. Give me a thumbs up if you follow me on that rationale, or stop me if you don't, because you should be able to put together the structure here and say, well, you know, it's got an HDI of 4. It's got aromatic, so that takes care of all the double bonds. Then I have an isopropyl group. I put everything together. I've got 9 carbons. I've got 12 hydrogens. It matches the NMR. So there you go. So you've solved your first NMR spectra problem. I could make this maybe a little prettier here. Let's fix these double bonds. There we go. Maybe something like that. There you go. So you remember this compound has a common name. It's called cumene, or you could call it isopropyl benzene, and that's fine too. All right, let's look at B. Anybody have any ideas about B? Do we have a tert-butyl, what was it? A tert-butyl, an ethyl, or an isopropyl? Do you see any of those in this compound? Anybody see any of those? Hey, man, somebody got both of them at once. Sean. Okay, so Sean got 2 in 1, right? So Sean, you're right that if we look at this one here, okay, and something I didn't do the last time that maybe I should have is count the number of the peaks. Right, you've got 1, 2, 3, 4, 5, 6, 7. So this is a septet, right? And it integrates for 1 proton. And then if you go over here, you've got a doublet here, and that integrates for 6 protons. So this is a doublet. So that means you have an isopropyl group in your compound. So I like to write down everything that's in the compound. So we have an isopropyl group. And then Sean also said we have an ethyl group in there too, and he's right. If you look at this, here we have a quartet, right, that integrates for 2 protons. And then here we have a triplet that integrates for 3 protons. And so we have an ethyl group. So we could scribble that down, CH2, CH3, like that. Okay, so there you go. So now we've figured out we've got an ethyl group and we have an isopropyl group in this compound. Is everybody with me on that? Ethyl and isopropyl. Does everybody see that far? Yeah? Okay. Any questions about that? Because I'd like to keep going with this problem for just a second. Okay, so let me erase some of this spinach here. So we know we've got an ethyl group and we've got an isopropyl group in the compound. I'll just erase some of this stuff here just so we can think clearly. Oops, didn't mean to erase that. There we go. Okay, so we've got an ethyl group and we've got an isopropyl group. Now, if we calculate the HDI of this compound, is anybody able to calculate the HDI of this compound? HDI is equal to 1 in this compound. Okay, so you have to use the formula and you have to have the formula memorized. We went over this in chapter 14. So the HDI is 1. Now, what are the possibilities here? The possibilities, if you have an HDI of 1, are that you've either got a ring, okay, or a pi bond, You know, those are the possibilities. But if I have two oxygens in the compound, what are the possibilities? I could have two alcohols, I could have two ethers, right? Or a double bond, something like that, right? But if we think about, you know, if we look at this methine up here, right? This is a CH. It's got a chemical shift of about 5. So how do we have a methine that has a chemical shift that high? Right? If you remember, the baseline of a methine was what? Does anybody remember that? If we go all the way back here, excuse me, to when we were calculating or predicting chemical shifts, so way before integration was here, okay? And we looked at this table right here. And we said the baseline for a methine was 1.7. Okay, so how would you get it up all the way by 5? That's a lot of deshielding. And so the way that you would get it all the way up near 5 is that you would add 3 to it. So that means that methine must be next to an oxygen of an ester. It's probably what it is. So if we go back here, okay, let's go back to the problem. So that means that if you draw an ester functional group like this, that means that our isopropyl is going to be here and that our ethyl group is going to be over here. So we'd end up with, this would be called isopropyl propanoate is the name of the compound. So I'm going to come back to this compound in a couple of minutes, okay? We're going to talk more about these chemical shifts for this compound, but I want to move on from here. Actually, you know what? Let's just solve it right now. So if I look at each one of the protons in here, right, and I try to predict what the NMR is going to look like, right? For the methine, I have the baseline of 1.7 parts per million, and then I add 3 to it, right? So I end up with 4.7 parts per million is my prediction. Well, you can see I'm up around 5, so that's a pretty good prediction. Then if I look at these two methyl groups here, okay, so I start with the baseline of a methyl, which is 0.9 parts per million, and then I'm going to add 1/5 of 3 to it. So what's 1/5 of 3? It's 0.6, so I add 0.6 ppm, and that gives me 1.5 parts per million. Now you can see that the methyl protons are not all the way up to 1.5, but they're deshielded for sure. There's some deshielding effect, okay? Then if I look at these two protons, these methylene protons, the baseline of a methylene was 1.2, and it's alpha to a carbonyl. And you remember that the deshielding effect there was 1. So if we add 1.2 plus 1, we get 2.2 parts per million. And what do you know? We're around 2.1, 2. That is a very close estimation. And then for the last ones, for this methyl group here, we say we go with the baseline, which is 0.9 parts per million. And then we have 1/5 of the effect of the withdrawing group of the carbonyl. So 1/5 of 1, so that gives us 0.2. So we add 0.2, and that gives us 1.1 parts per million. Well, you can see that this is bang on at 1.1 parts per million. So you see that the structure that I've drawn is consistent with the NMR spectrum that's shown here. All right, very consistent with the NMR. So this would be the correct structure for the compound. So if we just go back and review some of the concepts, okay? So you have to know that when we're dealing with chemical shift, that when you have an electron withdrawing group, it deshields the proton, which means it removes electron density, which means that the proton is going to feel more of the externally applied magnetic field. So it's going to have a greater energy gap between the alpha and the beta spin states. And so it's going to be downfield, right? It's going to be higher energy. So it's going to be more deshielded. So you can see the electron withdrawing effect of a halogen. We covered that last class. And then after that, we looked at the electron withdrawing effect of an oxygen, of an alcohol, or an ether. And we said that if you're right next to that, the effect is 2.5. And if you're next to the oxygen of an ester, the effect is 3. If you're in the beta position, it's 1/5 of that effect. And then we said if you're alpha to a carbonyl, the electron withdrawing effect is 1 part per million. If you're beta to that, it's 1/5 of that. So you need to be very well aware of that. We talked about diamagnetic anisotropy, which tells us or explains to us why aromatic protons have a chemical shift of around 6.5 to 8. I said 7 to 8 earlier this morning. It's close enough. And even though I'm going to give you a version of this table on the quiz, you still want to familiarize yourself with it, because I'm not going to draw the functional groups, right? The table that I give you in the quiz is this one here. So it's this table here, and you can see that in the table, I don't show you the structure of a phenol. I don't show you the structure of a vinylic proton, or what a vinylic proton or an aryl proton is, or anything like that. You have to know that. Okay, so you've got to familiarize yourself with the table, and we're going to look at carbon-13 in just a little bit. All right, so that's a little bit more review. So you want to, again, familiarize yourself with this table, and that will enable you to predict chemical shifts. And so that's why when we looked at this problem down here, 15.17, where was it? All the way down here, that we were actually able to incorporate HDI and the alkyl and aryl groups, and we were the functional groups and everything, and we're able to put together a structure that is consistent with the NMR spectrum. And this is something you're going to be asked to do on the quiz, on the final exam. If you want to take a MCAT, they're going to ask you to do all those kinds of things. So section 15.8, now it says here skip. Now let me just cover this whole thing here. The reason I put skip is because I don't ask my students to draw an NMR spectrum. Even if you're taking the paper quizzes version in the fall or the spring, I don't ask my students to draw NMR spectra. I tried it before, but the reason I don't is because it's very difficult to grade. It's very difficult to tell when somebody's trying to draw a quartet or a triplet. However, if you look at the suggested practice problems that I've chosen, that was chosen by your instructor, you'll notice that I picked some problems that involve this concept. So I think it's a good idea to try it, but I will not ask you to do it. Okay, it will help more your understanding of the N+1 rule and chemical shift and integration, but I don't ask my students to do that. So something that I tried to explain to you at the very beginning of this chapter was, if you run an IR on some compounds, like let's say you have these 3 aromatic compounds here. These are all xylenes. This compound here, this is called orthoxylene. I guess I could write it out. It's called orthoxylene. This one here is called metaxylene, and the last one is paraxylene. Anyhow, but you can see that all 3 of these compounds are isomers of each other. And if you tried to run an IR on these, you are not going to be able to tell the difference between these anyway at all. Okay, or it's be very difficult using the fingerprint region. MS, the same thing. They're all going to have the same molecular ion, but you could tell the difference between these using proton NMR in a matter of seconds. Okay, proton NMR, because if you ran the first compound, it gets 3 signals. The one in the middle gets 4, and the one at the end gets 2 signals. And again, you need to understand where the 3 signals come from, right? You need to be able to look at this compound and say, well, there's a plane of symmetry running through the compound here. If I rotate this 180 degrees, I would never be able to tell that I had rotated the compound. And so you see that the 2 methyls are chemically equivalent to one another. You see that these 2 aromatic protons here are chemically equivalent to one another. And then these 2 protons are chemically equivalent to one another, right? You've got to be able to do that. If we go to the second compound, okay, the same thing applies. It's got an axis of symmetry. I'm not going to draw, well, I guess I could draw it in here. Okay, you get an axis of symmetry that runs through the molecule here. If you rotate that 180 degrees, okay, you can see that you have 4 signals. And then the compound here has 2 axes of symmetry, doesn't it? It's got one going this way, and it also has one going through the molecule this way. So you've got 2 axes of symmetry, and so you only see 2 signals here. And so again, you can differentiate between these compounds very quickly using proton NMR. So let's get some practice on distinguishing between compounds. So the question is just, how would you use proton NMR to distinguish between the following compounds? So if we look at A, okay, if we look at A, so these 2 compounds in A, could anybody tell me, let's just start with the one, I'll put this in a blue box. Okay, let's do it this way. Could anybody tell me how many signals would you see in the proton NMR spectrum? I'm not asking you whether they're singlets or doublets or triplets. That's not what I'm asking. But how many total types of protons are there in here? Could anybody answer that? How many types of protons are there in this compound? Yeah, absolutely. There are 3, aren't there, right? So why do we know that, or how do we know that? Because there's a plane of symmetry running through the compound, isn't there? And so you see that this methylene and this methylene are chemically equivalent. We see that this aromatic proton and this aromatic proton, those are chemically equivalent. And we see that these 2 protons, these 2 aromatic protons here, are chemically equivalent. Does everybody understand that? Are there any questions about that? Do not hesitate to stop me. Does everybody see the plane of symmetry and how? Okay. All right. Also, you need to be, at this point, you should be very rock solid on your bond line structures and say, well, there's 2 protons here, right? There's 1 proton here. There's 1 proton here. Now, let me ask you about the second compound. So in the first one, we see a total of 3 signals. So we'll scribble that down, 3 signals. Are there any planes or axes of, axes of symmetry in the second compound? So this compound here, are there any axes of symmetry in here? No, none whatsoever. So could anybody tell me how many signals you would see for this compound? And just go with your gut. It's not a trick question. There's no trick here. Somebody says 6. I agree with that, right? All of these protons are unique, aren't they? Right? We have a we have an aromatic proton here. We have another aromatic proton here. Those are not chemically equivalent. This aromatic proton is not chemically equivalent to anything else. What if I get out the old purple pen here for a second, right? This is a unique aromatic proton. This is a unique methylene. And then I have this as a unique methylene as well. And so for this compound, I see a total of 6 signals. 6 signals. And there you go. That's how you would differentiate between the 2 compounds. Done. That's it. It's over. Everybody, give me a thumbs up if you're with me on that one. Because the next one's a little more challenging, I think. Okay, cool. So let's look at the next 2. What functional group is found in the compounds in B? What functional group do we have in the compounds in B? The same functional group in both of them. Exactly. So they're both esters. Okay. So they're both esters. Good. Now, if I look at this methyl group on this first ester on the left, okay, what kind of splitting do I see for that methyl? Does it give you a singlet, doublet, triplet, or quartet? Is it split by any protons whatsoever? What would I get for this? Would it be? I'd get a singlet. Exactly. Okay, so I'd get a singlet because it's not split by any protons at all. You can see the neighboring carbon has no protons on it, so it's not split. Now, what kind of group is this here? Hopefully you recognize this as a tert-butyl group. Everybody with me on the tert-butyl group? So if we have a tert-butyl group, we know that tert-butyl groups always give a singlet. There's no exception to that because it cannot be split by any protons. This carbon in red has no protons on it. So those 3 methyl groups are all chemically equivalent. So we have 2 singlets. Now, if we look at the next compound, we see that this gives you a singlet. This methyl is not it's not split by anything. And we see that this tert-butyl group is a singlet. Okay. The difference between the 2 singlets is the singlet in blue, both of them integrate for 3 protons, and the singlets in red, they both integrate for 9 protons. So we cannot use splitting and we cannot use integration to differentiate between these 2 compounds. Okay, splitting doesn't work, so we can put this here. Splitting, or n+1 rule, can't use it. We can't use integration, so we can cross that up. So what is the technique, or what information are we going to have to use to differentiate between these 2 compounds? Could anybody tell me? Remember, in a proton NMR, there's 3 types of information we get. Splitting, n+1, integration, the area under the signal, and what's the third thing? How are we going to differentiate between these 2 compounds? We're going to use what? Starts with the letter C, ends with chemical shift. That's right, chemical shift is what we're going to use. So chemical shift. So let's look at this. So I'm going to circle this singlet in black. Okay. So what's the chemical shift of that singlet in black? What I'm going to do is I'm going to start, since it's a methyl group, I'm going to start with a baseline, which is 0.9 parts per million. And how many parts per million am I going to add to it? I'm talking about this singlet right here. How many parts per million am I going to add? It's alpha to a carbonyl. So what do I add to it? Could anybody tell me? How many parts per million do I add? If we go back to the table, if you're alpha to a carbonyl, no, not 2. So let's go back. So if we go all the way back here, no, that's not it. It's here, okay? If you're alpha to a carbonyl, we add 1 part per million. So let's go back to the problem, which was here, okay? So if you're alpha to a carbonyl, so this is the alpha position to the carbonyl. So we take 0.9 and we're going to add 1 part per million to it, and that gives us 1.9 parts per million. Now I'm going to circle this one maybe in green or something, okay? My green pen, okay? This singlet, so this is also a methyl group. It's going to have a baseline of 0.9 parts per million, but how many are we going to add to it? It's next to the oxygen of an ester. Could anybody tell me how many parts per million will I add? 3. Exactly. That gives me a total of 3.9 parts per million. That's a huge difference in these two chemical shifts. And so the way that you differentiate between them is that in the compound on the left, you get a singlet that integrates for 3 protons at 1.9 parts per million. And in the compound on the right, you get a singlet that integrates for 3 protons at 3.9 parts per million. And that is how you differentiate between these two compounds, is using chemical shift. Everybody with me on that? And when I say that, it doesn't mean you just have to give me a thumbs up. You stop me if you're not following. Does that rationale make sense to everybody before we move on to the next problem? Okay. All right. One person. Okay. Well, if you don't understand, don't hesitate to interrupt at any point. You should be on Likes talking about organic chemistry, so you're never bothering me by asking me a question. Now, if we look at C, if I call this compound 1, let's not do that. Could anybody just tell me how you would differentiate between the two compounds in C? Either unmute their mic or type it in the chat. How would you differentiate between these two compounds? By the number of signals, right, Eric? Well, Eric, how many signals are there going to be for the compound on the left? 2, exactly. You have these 2 methylenes, which are chemically equivalent, and then you have these 2 methylenes, which are chemically equivalent. And so we have 2 signals for this compound. What about the compound on the right? How many signals do we have for it? Yep, exactly. Thanks, Sean. Good. We get a total of, we get a total of 3 signals for this guy. So we'll put here 3 signals. There you go, done. And again, think about it. You could not differentiate between these using IR. It'd be very difficult. Mass spec, you could, but you can see how proton NMR is very powerful. All right, what about the last 2? Well, hopefully you're getting the hang of it by now. And you see that there's no plane of symmetry in the compound on the left, but in the compound on the right, we have a beautiful plane of symmetry here. And so in the compound that I've drawn the plane through, you can see that you have 1, 2, 3 types of protons here. So we would get 3 signals for this one. How many signals would I get for the compound on the left? Could anybody just tell me flat out for this compound here? How many total signals? Yep, Ariana, I love it. My Ariana said this many, and she said, wait, it's this many, and you're right. It's 5, isn't it? Yep, you're perfect. Yep. So you get 1, 2. Here's my purple pen. 3. That didn't work. Come on, purple. 1, 2, 3. And then, there we go, 4. And then 5. Beautiful. There we go. Thanks, Ariana. So we get a total of 5 signals for this. All right. So remember, whenever you're looking at a proton NMR, let's just review one more time. What are the things you always have to consider? You have to consider the splitting, which is the n+1 rule. You've got to consider the integration, which is the area under the curve, and you've got to consider the chemical shift. Okay, you can't always use each one of these, but you have to consider all 3 of these things. Right? Splitting, again, this is the n+1 rule. Right, integration, that's, you know, the step curves that we use sometimes, or sometimes it just tells you, you know, if you get 10.1, then you have to divide, but you know what I mean? We covered integration in detail. And then chemical shift, you should try to memorize them. I would try to memorize chemical shifts. So remember, for chemical shifts, you're going to use 2 tables. Let's go back and find out what the numbers of the tables are. So it's table 15.1 in table 15.2. That was pretty easy. So if we go back here, let's write that down. So for chemical shift, memorize, okay, table 15.1 and table 15.2. Okay, those are going to kind of be your Bible for proton NMR. Give me a thumbs up if you're with me on all that. Cha? Anybody with me so far? Okay, we're going to practice some more problems in just a little bit. But this is kind of the David Klein. I will not take credit for this. This is in your textbook. So this is Dr. Klein, who's he's younger than me, I think, or maybe the same age as me. Anyhow, he wrote the textbook. And this is kind of his approach, and I take no exception with this at all. I think it's a great way of doing it. If you ever noticed, he loves to come up with steps, like just follow these steps, you know. It's like Little Miss Sunshine, follow the 11 steps, you know, to success or whatever. But anyhow, he loves to do this kind of thing, but I think that students like it, so I'm down with it. So the first thing that he does, and I don't always follow his 5 steps. You'll see that Mr. Dion is guilty of not following these in the exact order, because sometimes I can't help myself. I just go for the low-hanging fruit, right? But anyhow, first thing he does is he says, calculate the HDI. So you need to use the formula for HDI to solve that. So what's our formula for HDI? I mentioned it this morning, but we didn't go over it. So it's HDI is equal to 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens plus the number of hydrogens, and then we subtract the number of halogens. So you need to know that formula. Next thing is you look at the number of signals. So we just got some practice in that. And integration, so are there 2 signals, 3? Integration, you know, is it 2? Does this signal represent 2 protons, 3 protons, 4 protons? Then he should say, I'm going to add here chemical shift. So and chemical shift. Okay. And then the next one is analyze the signal. I really like this thing here where he says draw the fragments. I like to do this kind of, I call it my laundry list. I write down a list of all the groups. So I'll say, oh, there's a terbutyl. I scribble that down. There's an ethyl. I scribble that down. You know, I think there's 2 methyl groups. I scribble them both down. And then you assemble the fragments into a complete structure. This is where I see some students do some wacky stuff sometimes. Not you guys, of course. But when it says here structure, can you please write this down in your notes? Let's just put here, one that makes sense. Okay, I see students sometimes writing down structures that make no sense whatsoever. I mean, you've got a hydrogen with 3 bonds to it. Whoa, 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 whoa. Okay, this is not making any sense. You get an oxygen with 1 bond. No, that's impossible. You know, you've got a carbon with 2 bonds on it. No, that's not happening in this class. So you want to make sure that the structure is consistent with all the spectral data. And there you go. So when it comes to making structures that make sense, remember that carbon always has 4 bonds. Okay, it can be 4 single bonds. It can be a double. It could be, you know, it could be a triple bond and a single bond, right? You should know that oxygen always has 2 bonds and 2 lone pairs. It can be 2 bonds, 2 lone pairs like this. You should know that nitrogen always has 3 bonds and 1 lone pair. It could be, you could have something like this, but we wouldn't see that. So you've got to use the proper bonding. The halogens, right? The halogens always have 1 bond, and hydrogen always has 1 bond. So make sure that your structure makes sense. You know, again, if you've got 6 bonds to a carbon or 1 bond to a carbon, whoa, 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 you're way off in left field. So make sure you propose something that is reasonable. All right, so there we go. Let me just see here. You know what I think we will do is we will take a short break. And what I would like you to do, so let me just see something here. Just bear with me here. I had a bunch of stuff set up for today. So if you go into the chapter 15 module, you'll see this thing here. It says Klein in class practice. So it says in class practice. You can see it in the top left-hand corner of your screen here. What I would like you to try on the break is just to try these 2 problems. Okay, I want you to try, and we're going to get into carbon in just a sec, but I'd like you to try these 2 problems, okay? And you're going to have to refer to table 15.1 and 15.2 probably to solve these. So let me just show you what they are. It says propose the structure of a compound that exhibits the following proton NMR data. So first you have the molecular formula, and you've got to calculate the HDI. So I'll just help you out with this one. It's HDI is equal to 1. So that means you've got 1 double bond or 1 ring in the compound. Now remember, the little delta signal here, that represents chemical shift. So what this is saying is, so I'll just scribble it up here. So delta, that represents chemical shift, which is always, always, always recorded in parts per million. So what this is saying is that at 1.09 parts per million, you have a doublet that integrates for 6 protons. At 2.12 parts per million, you have a singlet that integrates for 3 protons. And then at 2.58 parts per million, you have a septet that integrates for 1 proton, right? That's the kind of rationale there, okay? And so for the next problem, at 0.91, you've got a triplet that integrates for 3 at 1.19. You've got a singlet that integrates for 6, so on and so forth. Okay, so we're going to take a short break now, and I would like you to try both of these problems, and we're going to come back and solve them. And then I'm going to go over carbon 13 with you, which is a much shorter section than the section on proton. And then after that, we're going to spend the rest of the class just working on practice problems as a group. All right, so again, I want you to try these 2 problems during the break. So if you're watching the video, this would be a good time to grab a sheet of paper and give these the old college try before you go to the next video.